Oh, oh, yeah.
Okay, everybody hearing okay online? Awesome. And you can see the boards. Looks like good. Okay, so before going on, I wanted to to amplify a little a remark I made at the end. So I did an extensive study of the constant coefficient scalar convective heat equation here. I've rewritten it for you. Um, So convection rate A taken positive, and we did by relating to Fourier transform. And maybe I'll even skip ahead. And the way we did that, we moved a contour onto the dispersion curve and made some connections, which were not that easy to make, right? There was some algebra and so on. But I like those connections, but it's not necessary to do all those complicated things to get an estimate. We could directly work from the Laplace transform point of view. So the Fourier transform point of view was to take, so remember, we have the spatial eigenvalues. So for Fourier transform, we have the temporal eigenvalue lambda solving the dispersion relation. For Laplace transform, we solve the indicial equation for the spatial eigenvalues mu. Those were the growth rates in x. And okay, they solve a quadratic equation. This one's easy. We just put everything, we solve for lambda in k, it's already done. But this one we have to solve by quadratic equation. What matters is the small frequencies, small lambda, which corresponds to large time. This is what we want. Okay, so we can write it as a quadratic formula and expand, Taylor expand around the origin, and we get this expansion here. Okay, and we throw out everything above 2. And those are error terms and they can be accommodated. Uh, it's better to just start here, actually, because if one has a system, there's no quadratic formula, but you can still do expansion, spectral eigenvalue expansion. Okay, so we have this. And what we could do now is we took A positive, so we want x bigger than y, otherwise it's not very interesting. It's exponentially decaying in time, and we'll take it less than 0. Didn't really need to do that. I just need x greater than y. Okay, so then here we have, I'm going to point out that the natural Laplace transform curves are real part of lambda 0, so vertical lines, instead of real part of mu equals 0. So let's move the vertical line over just to the essential spectrum again and see what we get. This is the inverse Laplace transform. So here I've got lambda equals I tau because I've moved to the imaginary axis. So here's the e to the lambda t. Here's e to the mu times mu of lambda times x minus y. That's what we derive. We directly solved for the resolvent, and this was what we got. It's just the neutral decaying mode. Okay, and that's it. And I've neglected everything above third order. It turns out that can be, that gives faster, those errors those terms give faster decay. If we take the difference between this and other ones, that's a detail I'll avoid. But now I can rewrite this in the form of we know it's a Fourier integral to begin with, but I want to write it like this. And so it's a Fourier integral in t minus x minus y over a, and there's a Gaussian again. So the only Fourier transform fact that we need to do all this, the only thing we needed for the Fourier case was the fact that the transform of a Gaussian is a Gaussian, and that's all we need here too. So the transform of this Gaussian, the transform of a Gaussian with a coefficient c is the same thing with coefficient 1 over c. So I know that it's e to the, okay, minus t minus x minus y over a squared divided by, this is the constant in front of tau squared. So it goes like this. And it doesn't look very much like a heat kernel anymore, except that you see it's maximized near the center where t is x minus y over a. If we substitute in t, at for x minus y here and here, we get the correct, we get back the heat kernel. So up to a faster decaying term, you could just do it this way. And without any reference to the Fourier transform at all, other than the fact that the Laplace transform is a Fourier transform vertically. Okay, why do I not like this quite as well? Well, because remember, we're not actually going to follow this curve. We're going to only look at low frequencies. So at some point, we're going to veer off to infinity and just say these are exponentially decaying terms. Well, if I do that with the Laplace transform, now I actually am going to sometimes cross over from the positive side to the negative. And I have this other little branch I have to discuss. And of course, it has to work. These are the same, but we already have enough cases. So that's why I like the curves. We don't have to discuss that case. We just directly transform to the Fourier setting and get estimates. But okay. One more comment. This is exact inversion. We really don't, that's not really what we have going on. More generally, we have all of these things times something that depends on lambda. So, and x and y. So it's an oscillatory integral. And as t gets large, this oscillates faster. So it belongs to that category of problems. And what you want to do in for such a problem is, and I'm integrating on, now let's just talk about the vertical lines. Well, I should take the one, the estimates that I know how to do are usually just this. So I want to minimize that. So I want to minimize the maximum of the real part of phi, because that will give me, that's where my decay is coming from. And for the problems we have here, it's easy to see the maximum value always occurs on the real axis. And also, moreover, the decay away from the decay in tau, so we have lambda equals gamma plus I tau. That's my notation. Tau is the imaginary part. For us, it's like it has an e to the minus tau squared times a constant. It always has a Gaussian drop-off away from the real axis. And so that will always be integrable. So in fact, what we get when we do this kind of estimate, we just get a big constant times the value on the real axis. And there may, depending on powers of lambda. Okay, so powers of lambda, what do those do? Well, in the Fourier setting, that would be like a power of ik. It's a derivative. We know derivatives decay faster because of scaling principles, and the same principles will give us faster decay if we have powers of lambda. Okay, so and so that's how the terms I discussed so far, they're not like this. There were no, everything was in the exponential argument, and there was no lambda dependence here. But as soon as I take error terms and expand further, I will have dependence on lambda, x, and y. And okay, I could Taylor expand out and do explicit computations as far as you like, but at some point I have to estimate the tail. And the best way to do that, the sharpest way, is to move the contour to the place where I get the same estimate. And all I need is boundedness of A. So that's how we actually do it. And there, a subtle point. So let's see. So the picture is already here. Let's see. So if we're talking about where do we want to move the contour in order to get such an estimate for free without actually inverting anything, it was different real part of lambda, sorry, real part of mu equals alpha, and alpha was x minus, sorry, x minus y minus at over t, 2t. So we wanted to look at shifts in this parabola, and some of them go into the essential spectrum. All these kind of, if I'm going to move contours, I have to have analyticity. So this is like analytic stationary phase estimates. That's basically what it is. And it's very important to have analyticity and not just say you see infinity in lambda. That would not be good enough. Okay, and just yeah, it's yeah, steepest descent or Riemann saddle point, steepest descent. Yeah, this is what it, yeah, it's like that. And there's yeah, there's something, there's a nice I'm going to refer to paper. So let's see. So Lafitte, Williams, and I let's see, I wrote down this. This is really a side note, but I think it's interesting. I like it. It's in Siam Journal of SEMA 2015, and it's called um, uh, Block Diagonalization and C infinity versus C, sorry, C omega versus C infinity stationary phase. And it turns out you can, suppose you only have, okay, if you only have CR regularity, well, you don't get much, right? You just get algebraic decay, not exponential. But what if you have Gevrey regularity or C infinity regularity or something? In between, it turns out you can interpolate between C infinity and C omega by the Gevrey classes. And you can get a little more. That kind of surprised me, and I enjoyed it. That's completely off topic, but if you like stationary phase and steepest descent, you might like that. It's in the appendices A and B.
It's a new book.
Sorry?
It has a new book about
I didn't know that.
going to be published by the CRM in the Montreal.
Oh, great.
Stationary phase.
Uh-huh. Yeah. He's much more refined than me. I do macro local. This is macro. Yeah, he's a great expert in that. Okay, so that was just some kind of comments left over. Okay, so now we start the real business, and maybe I'm also trying to delay because this next part, now we have to calculate some things, and it gets a little bit messier. Okay, so variable coefficients. That's what we need. And so I'm going to go back and write the variable coefficients problem as a first order system. Let's see, this is how it looks. A bar, sorry, V dx. V equals 0 f. And we'll call this V, we'll call this script A, and we'll call this script F. That's how we write it. Okay, and the conjugation lemma now takes this to a constant coefficient problem. So we take TZ equals V. And we find that for appropriate choice of t, which is a exponentially decaying perturbation of the identity transformation, we convert this to the constant coefficient limit. And this is for x greater than or less than 0. So there are two. Really, they should have plus and minus symbols. Right? In fact, yeah. Well, it's sort of hard to read, right? If it's plus or minus, we don't know what that means. But okay, so let's try. Let's do this. This is for x positive and x negative similarly. And then we have z minus of 0 minus is capital M of lambda z0, z at 0 plus. And here M was t minus inverse t plus. That's what because it just reflects that the original v is continuous across the origin, but the new okay. The new variables, which are conjugated, they have different conjugators. There's one that's designed to work well out at minus infinity and one designed at plus infinity. At the origin, we don't really know what they do. All we know is that they remain invertible and, with a bounded inverse. So this M makes sense and it's analytic. Let's see. Which one should have a plus minus? Oh, yes. Right. No, let's see. Yes, you're right. This should be just a plus or minus. A plus. Yes. It's just the constant limit of a bar. No more a bar. A bar was a variable coefficient convection. Okay, so we've written this before, and we've even written the next thing. Okay, so we get z plus of x is e to the a plus x stable projector zs at 0 plus integral 0 to x e to the a plus x minus y stable projector forcing term, and then plus or minus integral x to plus infinity e to the a plus x minus y unstable projector f plus of y dy. And similarly, z minus. Okay, and now here's where when we came to this point, we were sort of describing it very abstractly or vaguely after that, but now we really have to do it. So z stable at 0 plus is to be determined. Z unstable at 0 plus. Okay, so if I apply the stable projector, the unstable projector, I kill this term because this is a complementary projector. I kill this term and I'm left with this term. If I evaluate at 0 plus, this is negative integral from 0 to plus infinity, e to the a plus x minus y unstable projection of f. And likewise, I do have z unstable of 0 minus is to be determined, and z stable of 0 minus is minus infinity to 0 e to the a minus y pi stable f minus of y dy. So that means, so now what I'm going to do is, let's see what happened. I lost the key point, which is, okay, I've solved number one, but I have some things left over still to do, right? What I have to figure out is what is z stable at 0 plus, and what is, and on the other side, I come out with a similar formula, but with z unstable of 0 minus. I don't know what those are, and I have to find them. The way I'm going to find them is using the matching condition. And so let's rewrite that. When we rewrite that, we have that using condition 2, I have z unstable of 0 minus, and then z stable of 0 minus, which is integral from minus infinity to 0 e to the a minus y pi s f tilde is equal to m of lambda times z stable of 0 plus and z unstable of 0 plus, which we know to be minus integral from 0 to plus infinity, e, didn't leave enough room, e to the a negative a minus y f pi unstable f tilde plus of y. Okay, so but the two things I want to solve for are here and here. And consistent splitting, which was an important assumption, says that the dimensions of stable and unstable subspaces are the same at plus infinity as at minus infinity. And therefore, the dimensions of these two sets of coordinates, these two coordinate blocks, add up to n. They add up to the full dimension. So I'm going to rewrite this as an equation for the two unknowns in terms of these integral operators applied to f. And just notice that these make good sense because this is a minus times y. Okay, here y is negative. Let's see. Hopefully I got this right. Maybe I have written it wrong. This is a plus. Okay, this is, I do seem to do some 0 to infinity. No, that's good because I have the unstable, so this is growing. I have a negative that makes it decaying. Y is positive. This is a nice exponentially decaying kernel applied against a function. So we discussed that before. Okay, so now I just rearrange this.
Is known at this level.
It's just unknown. We don't know. It could be anything. Yes, there's m of lambda. All we know is that it's close to the identity. Well, close in the sense that it departs by an exponentially decaying term in x and y. But x and sorry, in x. But x is 0. is not decaying at all. This could be huge, and it could be basically random. We don't know what it is. It depends on the dynamics of this variable coefficient flow coming all the way in from infinity. So we don't know much about it. The interest is very interesting that we don't need to know more. That's the funny thing about all this. But I'm going to rewrite this as, okay, so I want to rewrite it as an equation for z unstable of 0 minus and z stable of 0 plus, because those are the things I still need to find. Okay, so I rewrite that equation, and if I got this right, it's identity, well, it was just 1 in this case, m12, 0, m22, and then on the right I have negative m11, and I'm leaving out the lambda. Of course, m does depend on lambda, negative I 0. I think this is what I get. And then times these integral operators on f. Pi unstable f tilde what was it, plus. That's a plus. Okay, d of y dy, and this one was, it's not so important. It's just a, well, it will be important in a moment. A minus y pi s f tilde minus of y dy. Okay, so I have, and this is what I called before little m, and I asserted that it existed, but I didn't tell you what it looked like because it wasn't important before. We weren't computing anything, and it's still not important. What the only really important thing is the form of these guys, because this is a function of lambda. I think we called this n of lambda before. There's no x and y dependence on these. So when I invert it, I'll just get a bunch of an expansion in lambda times these decaying kernels. Okay. So where do I put this? I want to keep this for a second. Okay, so at this point, we're gonna give up the that's the one I didn't want to give up. I think this was what it was. EVA plus X, right? That's what it was. Just check that. Yeah. Okay, so it's the other one that I use. It's right. This I don't need. I've now put this into the equation. So I want to put these two together. And say that I get the following. I get z of x is equal to integral from 0 to plus infinity e to the a plus x pi s of, okay, now, what am I doing? I'm plugging in the first term, e to the a plus x pi s. But it's applied to v of 0 s. Z, I'm sorry, I've switched around to, let's see, why did I write v? This is a z. Yeah, this is a z, that's why. Okay, z. Yeah. So I'm just inserting in Z of 0 plus, ZS of 0 minus. And to get that, I invert things and I just say, I don't know exactly how it looks, but it's some combination of these two. So, and I'm going to choose, let's see, and I'm going to take X positive without loss of generality. So I'm looking only at the one that I wrote. And I have d of lambda over lambda e to the minus a plus y pi unstable f tilde of y dy. That would be plus. And then plus d minus of y over lambda e to the minus a minus y pi s f minus of y dy. I think I put my integrals in the wrong place. I want this is what I want. I'm taking the first term and just plugging in for z of 0, z stable of 0 minus, and that is some combination of these two. And what am I using? Okay, now I'm using the fact that m is invertible. The determinant of m is the Evans function. And I assumed a single 0 at lambda equals 0. That was my spectral. This encodes the point spectrum of the solutions of the eigenvalue problem. And I've made the assumption that there's that the translational eigenvalue at lambda equals 0, which implies there always is a 0. M does vanish somewhere at 0, always. But I'm assuming that it doesn't, that it's a simple 0, which means there's only one 0 of this determinant function. And elsewhere on this is on all of real part of lambda greater than or equal to 0. So in the whole non-stable half plane, this is non-vanishing. And that means also by openness of analyticity, we can move, it's also true for real part of lambda bigger than or equal to some small negative number. We also have that. So that is why I have a 1 over lambda here. So d of lambda is analytic, but this is a meromorphic function. When I invert a matrix, I get 1 over the determinant arising in there. So I get a matrix of cofactors, which is analytic, divided by the determinant, which is vanishing to order 1. So that's why I can write this. And amazingly, it's all that I need to know to get my estimates.
So what conditions, what conditions tell you about this?
Well, so I don't directly impose anything on big M. It's only indirect. I just make assumptions about the existence or non-existence of point spectrum. For the original variable coefficient problem, because that is encoded in here, right? If I put f equals 0, it changes from the resolvent equation to the eigenvalue equation. And now I have non-trivial solutions if and only if determinant of M vanishes. So the zeros of M are the eigenvalues of the problem. They're the eigenvalues. They coincide. Although if I don't have vanishing of this determinant, I just invert this matrix and I find out that these are 0. I plug them back into my formula here and I see, well, if there are no f's and if zs of 0 minus and zu of 0 plus vanish, then z vanishes on both sides. So that's only the trivial solution. So yeah, the price that you pay in doing this conjugation is it obscures the link to the eigenvalue equation. So you have to remember what is yeah, but it's all encoded in this determinant here. But we don't need to know much. This is the amazing thing. We only need to know that it's meromorphic and its only pole on the non-stable half plane is at 0 and it's simple. Okay, so but by the way, that one, having a simple pole, that can be sort of non-trivial if I were dealing with systems. And that's something I'll talk about after the break. But that yeah, there is some information encoded in that assumption. But I don't directly try to figure out what capital M is ever. I think that's, you know, other than numerically, that's basically impossible. It's the same as finding an exact solution of the variable coefficient problem. Yeah, so yeah, kind of the point of view here is that let's find out what information we need to know in order to get estimates. And later we'll try to verify that information, but we try to use as little information as possible. And it turns out we don't use very much here. All we're using is information about the Evans function. And that, except at the origin where it's embedded in a central spectrum, it's just an eigenvalue problem. And we're dealing with, right now with a second order scalar eigenvalue problem. So we can pretty much solve that. We know where the eigenvalues are. But what we don't know is the order of vanishing at 0 is a little tricky, but we're going to discuss that later. Okay. And there's more. That's kind of that's the trickiest term, but there's another term, integral from 0 to x of e to the a plus x minus y. There are two more terms, right? That was just the first term. And then minus the integral from x to plus infinity of e to the a plus x minus y pi unstable of f tilde plus of y dy. So, but I'm going to divide these up. These terms I'll call free transport, because these can be recognized as exactly the terms we found for the heat equation, for the constant coefficient problem. They're identical. So we actually already know what these give. Exactly. They give it a transported heat kernel. And these, okay. These we'll say these are interaction terms. They have to do with interaction with the boundary, and the boundary really means the shock, the dynamics of the shock wave. So I always draw this picture of sort of some kind of imagined shock layer where things are basically constant outside it and then varying inside. And we have a heat kernel that comes into the shock layer, and then something happens. Well, for more general cases, it could emerge or transport. Here, both sides are coming in. In the scalar case, not very much happens. They just come in and they disappear. But they don't completely disappear. They can have an effect. They can excite a bound state, a zero eigenvalue. And that bound state corresponds to shifting of the shock. And if you think about that, it's very sensible because this is depositing mass. And we have conservation of mass. Mass came in from both sides. How can that be accommodated? Well, only by shifting the shock. Otherwise, it doesn't make sense that the time asymptotic behavior could be the original shock. So it's very sensible. Okay, but we have to estimate. So I claim we've already estimated these terms by doing the constant coefficient case. There is a subtle issue, though. This is in the z coordinates. This is exact in z coordinates. When we go back to the original v coordinates, there's a conjugation, which is almost the identity, but it has some exponentially decaying terms in x and in x, and so that will introduce error terms. So whereas before it was a combination of well, we get from our expressions, we get both formulae for v and for z and zx, z and its derivative. And that's fine, but from that, in the constant coefficient case, we know derivatives decay faster by a factor t to the minus 1/2. Here, we don't quite know that. We know that derivatives have a bound of t to the minus 1/2 times the heat kernel plus e to the minus x, so some constant, so an exponentially decaying term in x times an undifferentiated heat kernel, because they mix. And you could think of it in a different way. If you have a conjugation directly in front of z, well, you can also just use the gap lemma to write v itself as z times 1 plus exponential decay. If you just differentiate with x, you'll see the same thing. It's just, does the derivative fall on the heat kernel or does it fall on the conjugator? If it falls on the conjugator, you get an exponential decay, additional exponential decay. If it falls on the heat kernel, you get additional temporal decay. So that's something to keep in mind, and that we're going to put in the final estimates. But okay, but now here, what about this? This is a little different. So we have mixing between different terms. Okay, so the ones that matter, the terms, all these are nicely exponentially decaying. Remember, there was a fast decaying mode, mu plus, and a neutrally decaying mode. And the fast decaying mode was, it's bounded, it has uniform exponential decay. We can move it off to negative infinity and get rid of it up to a time exponential decay term. So the ones I really have to estimate, the key term, so we have to keep the mu minus of lambda term. And that was the one that was negative lambda over a plus 4 lambda over a cubed plus 4 lambda squared over a cubed. That was the neutral one that vanishes at the origin, the one that gives us back a heat kernel. Okay, and what we find we have to estimate are terms like, well, the key term is, okay, the most important term is the one with e to the minus y, mu, e to the mu minus of lambda y, and e to the mu minus mu plus of lambda x Okay, this is the key term. Where this is fast decay and this is slow. Okay, what do we do with this? Well, we replace this by mu plus at 0. And we can accept, and there's a Taylor expansion, but the Taylor expansion is harmless. We'll get another similar term with an extra lambda that cancels this. It's no longer the same size. This is a residue type term. This is going to be a non-decaying term. As soon as I get rid of lambda, it's like a heat kernel, but better because it's fast decaying in X and only slow decaying in Y. So I replace this here. This one, and I should have said D, okay, and I have D0 plus lambda, D1 plus dot, dot, dot over lambda. And I'm going to get rid of this one too. Same reason. Any lambda term I can discard. But I can't discard this because I have no decay otherwise. This is constant. If I just put in mu minus of 0, that's 0. This would be very bad. So this is what I want. Okay, and then, okay, but I observe that this gives me a residue. If I take this contour and pull past the essential spectrum and off to infinity, I get a residue, and the residue I get is actually 1, just a constant, times some decaying term. But that's the spectral projection onto the 0 eigenmode. And we know what the right eigenfunction should be. It's the derivative of the traveling wave. So actually, this one I can replace by so e to the mu minus of y dy d lambda by dx w bar. Okay, and sorry, I'm changing back. I'm also changing back to the v coordinates. When this is in the z coordinate. When I change back to the v coordinate, I know that this one is what comes out of the pole of the resolvent, and that is the eigenprojection. And the eigenprojection is onto dx w bar. So now I'm putting back in some of the information that I took out, and that's crucial. I'm taking lambda, sorry, I'm taking y on minus infinity plus infinity, and I'm taking gamma minus I infinity to gamma plus I infinity. And I'm going to decide what gamma should be. Yeah. Yeah. And, oh, but, very important, this is a 1 over lambda. Okay, and so, but now, what I'm going to do is, now this is a Fourier integral, basically. I mean, there is no dependence on lambda except in the exponents. So I can now I'll move this to the dispersion curve, as I did before, and reduce to a Fourier integral, Fourier transform integral, and it becomes integral from minus infinity to plus infinity of e to the I k y e to the minus, okay, so a k a I k plus k squared k over, this is times t over k over ik, getting rid of the I there, 1 over 2 pi. And this is, if I didn't have the 1 over ik, this would be a heat kernel. I have a 1 over ik, so what does that do? It's like integration. I'm integrating a heat kernel. And I get a Heaviside function. Not a Heaviside function, I get an error function. But I have to be a little careful with this because it's going right through an eigen, I mean, it's going right through a pole. So it'll return a constant. And I need to know what the constant is. But I can easily figure out the constant because I know that if I move x out to, y out to negative infinity, it vanishes. And so I can just say, well, let me find the derivative of this function, which means I just get rid of this. And that's a heat kernel. Now I integrate it. I find it's an error function plus whatever constant. And because I know that it must vanish at negative infinity, it's error function of y, let's see, y minus a t, y plus at because of the minus sign. Over square root of t, an error function defined as integral from, see, I want this to go to 0 at minus infinity, so minus infinity to x of e to the minus z squared 2 dz. So it looks like 0 to the left and then 1 to the right. So it's kind of like a smooth step function. Now let's go back to my picture. Oh, and sorry, all this times dx w bar of x. So what happens at t equals plus infinity? This part just goes to 1. So the time asymptotic behavior I better go over here. I get just d naught dx w bar of x. And this is the thing that's going to be, this is the thing that's going to be integrated against the forcing. F of y dy. So it's like, it's a projection. It looks exactly like what we did in the case with the spectral gap. This is a constant. This is an unbounded projector on L2. This is just a constant against an L2 function integrated from minus infinity to plus infinity. That's not bounded. And that is a consequence of the fact that we have, it's embedded, it's a pole embedded in the essential spectrum. It doesn't behave quite the way we expect it to. Although this is pretty close, right? Because what belongs here? This is the right eigenfunction. This should be the left eigenfunction. And it is. It solves the adjoint eigenvalue equation. What's the adjoint eigenvalue equation? It is d lambda v tilde plus a bar dx. So the order of dx and a reverse, and there's a sign change. That's the adjoint equation. Notice that constants are solutions when lambda equals 0. So this is the 0 eigenvalue equation, the left eigenvalue equation, and it admits constants. So this is, and that's the only the only bounded solutions are constant solutions. So it's very clear in this case what it should be. Less clear for systems, as we'll see later. But this makes perfect sense. But it's no good for a stability analysis. So we're not going to use this. We're going to use this. And this is, instead, of this, we substitute L of y t against f dx w bar, where this L is the error function. This will be L of yt. I left out a d naught. There was a d naught in front of that. We are calculating, we've got this new kind of term. We had an old kind of term which was just free flow, like a constant coefficient flow. Let's see. It is where did I write everything? I think it's no, because this was let's see, this was old. This we've left behind. This is not anymore a formula. I mean, that's what we started with, but we got, where did we go? We went passed through, maybe we lost a board that we kind of need, but it's, yeah. Okay, I don't have that board there where I combined everything together. But what came out of it was the free flow terms. Yeah. I hope I didn't just erase what I needed. No, this is old. I think I lost that board. But what came out of it were things that looked like the constant coefficient problem, and then one other term really that was important, and that was this term, which was where we mix now the effect of the interaction of the boundary. So solving the problem with the matrix little m to find the boundary values led to terms with different, see, for the free boundary flow, we have like a mu minus times x minus y. It's like a convolution term. This is no longer a convolution. It has two different decay rates, different ones on x and y. And we have to figure out what that does. It's pretty easy for us in this case because we were able, this one we know it's basically in disguise, it's dx w bar. So we just pulled that out of the integral. And that's why we were able to just look now at a single, now it looks like constant coefficient again, but with only y, not x minus y. And that's why we got an error function in y. So this was what I call the interaction terms that involved both sides and different decay rates. And this was the only one that causes any trouble. All the others are harmless. Yes, the first term that I wrote. Yeah. And I only took out one piece because there are many, right? It was well, this would be the let's see, this is the minus lambda over a. So this is, yeah, this is the this is the growing, this is the unstable term, this mu minus times y. This times y, not dy. This was the slowly growing terms. That was the unstable projector. There were others, but they were not harmful. Only this one is, and this is the only one that has a pole. Also, okay, you're calculating basically the residue, yes, but except yeah. No, except no, I'm not taking the residue. If I went all the way to infinity, that would be a choice of contour, and I would get the residue plus whatever is over here, but it would be very small. But I'm not happy with that residue. It's not good enough for me to do analysis because it's that would be this one that I'm trying to say is this is what we would have if we went the old way. Like we want to sort of we think there's maybe a non-decaying part and a decaying part. And this would be the first guess for the non-decaying part. But actually, the difference between these two is also non-decaying. Because the difference between an error function and a constant is still got big support. So it would really depend on f and where it's located. If f is located off to toward minus infinity, then this would still have a big, the difference between the two would be large. It would be almost as, it could be as big as f, L2 norm. No, I'm not going to even do, I'm not going to do that. What I'm going to do is in my analysis, I'm not going to use this as my non-decaying term. I'm going to always keep it like this. I'm going to substitute this where I used this term before and try to remove it from the calculations. I'm going to remove this one instead. Because, let's see, for zero mean value, this should be, this would be okay. I think it might be okay. I'm not sure, but that makes some sense to me. Oh, it would be zero. Yes, right. Yeah. Even, but maybe I would still, I'm not sure because I still, I mean, it would be, oh yes, it would be identically zero. Yeah, sure. I mean, zero would be good against a constant. Yeah, that's true. And also in the history of this stuff, people did mean zero perturbations earlier. And yeah, dealing with mass is something that's harder. Okay, let's see. So this is time to stop. So let's come back. Let's take a break and come back. And okay. For oh, yes, for so yeah, for this one. Okay, so there's yeah, in some references for sure. Okay, there's I did this analysis in there's a quarterly. Let's see if I can find. I wrote down the dates and everything, but now I'm not seeing them. Um, hmm. Well, okay. Quarterly applied math. I think I have only one about nonlinear stability, and this is for Berger's equation. So I wrote out the whole thing. You can do the green, you could do explicit Hopf-Kohl transformation, a linearized Hopf-Kohl, and explicitly find the green kernel. And you see that it has the same error bounds that I'm giving, but you don't have to do it. And then I do the nonlinear analysis. But maybe more interesting is Yingwei Liu, also quarterly applied math, did the green functions. And I think this is about 2016, these two. But you can also look in, I think, Masha and I in 2002. This was for relaxation. And I think 2004 was for real viscosity. So we did these arguments. So these are harder cases. So that's why I would recommend looking at the scalar to see how it goes, the scalar case. And especially Yingwei's treatment is very nice, I think. Okay, so Any questions from online before we break? Okay. All right. Let's stop for a bit.
You can put it, your talk, I mean, I put your talk on the 6th of March.
Thank you.
So when it's urgent, it's, yes, not super, super urgent, but that we have the date.
Great.
So that's good. So when do you leave here now? You're going back to,
Going back, we haven't quite decided, but I have to be there from like the 19th, 26th. This re-interviewing a director from Roger's Institute.
because Roger was a director of the institute
Yeah.
for many, many years.
Yes.
Did you get any news from him? Or not really?
No.
They were,
Family would be private guy, but so Teresa Bongay is secretary, communicating with the family for a long time. She's like, it's part of the family. It's quite like secretary.
secretary of your, in your department?
Yeah, she was a secretary for the institute. So
In your department.
yeah, and within our department.
There was one student that I met recently.
Oh, yes, yeah, great.
So,
This
yeah, it was-
young woman, right?
Yeah.
Yeah.
And it we met because when I was there, she was making people do it. And I wrote to her, and I wrote to her. She got to the hotel. No, she just like and the time. So she told me each time she does something.
Yeah, right.
So
Their lives by the letters. Yeah, no, she was talented as a. And of course, she had many good students.
So
Did you go to Denise, Sarah? Was his good? Isn't that funny? I didn't know that for a long time.
yes, but he had so many.
Yeah.
So many.
Carlo Rosa, that's Rosa.
And in the order. So, but in the order.
Yes.
Colette.
That's right, yeah, he was really very successful.
From the, you know, for Una.
Yeah, I hope we can get. Person, the delegates, get the person. Free.
Yeah, I think
Second
they
one, huh?
2 hours, right?
Well, we were already lost. We were more lost. It's complicated, no? I cannot even take notes now. Federico, we just write the test, I mean, questions, just kind of the same, but a little bit different. And I will pass it to you just to look and we can submit, because I received this.
Oh, the
ATS
student,
student.
okay, okay, yeah,
I can take your template, right?
yes,
And just change the question.
yes, yes. And then you can send it to me, so I put it on CrowdMark and I make the booklet for the student and we're good. Yeah. Yeah, it's not a big deal.
No,
It's
it's not
just-
big deal, except that already in 3 weeks is the next.
But
Time is rushing.
he said that,
Well, I don't know if he's even come.
yeah, he said he has to ask with
Yeah, we don't.
2 weeks notice. I don't know.
I don't know if he's coming to class. I don't remember. Haven't seen his name.
Well, nobody's coming to my office hours.
I have maybe one or two, but when they come, they just stay too long.
Now, typically, I send them away. I tell them, okay, shoot, have no longer any question, go.
Only two are trying. Well, it's okay. I'm glad for you.
No, I mean, I'm happy when they don't show up, it's bad. You know,
I'm talking about office hours, and they don't show up. It's good. If they understood everything.
well, I think, they already know.
That means they're perfect, right? If they don't show, everybody's happy. So, okay,
Let's wait for the grades.
yeah. Okay, so I've only given some sketches of the key elements here, but here's the theorem that we get in the end. And I will say a few more things, how they come together. For the scalar viscous shock, Laplacian viscosity, assuming a simple root of the Evans function, which is defined as the determinant of our little m of lambda at lambda equals 0. Okay, and actually, that's not hard to prove, but we didn't prove it yet. And no other roots on real of lambda bigger than or equal to 0. Then the solution operator splits as S of t equals S high frequency of t plus S tilde of t plus E of t. And E of t is dx w bar L of yt against, it's a projector, and then times a smooth cutoff for t bigger than or equal to 1. Okay, where okay, so S high frequency applied to F in L2 is less than or equal to a constant times F L4 e to the minus theta t. That's like the high frequency part we took off in previous estimates. And okay, and S tilde of T F L2 is less than or equal to a constant F L1 intersect H4 1 plus T to the minus 1/4. And the derivative estimate, L1 intersect H5, 1 plus T to the minus 3/4. And right, and here, and E of T, let's call this, okay, so E of T defined as little e of T times dx W bar of X, sorry, dxW times little e of T satisfies E of T F. Okay, so let me be careful here. Well, I'll just say no, that's actually right. That's correct. Satisfies E of T F.
Lowercase e is essentially that project times the.
Yeah, chi t greater than or equal to 1 times L of y t against F. Yeah, so that's a number. It's not a function. And that one satisfies, okay, here we go. This is less than or equal to a constant times F L1 and E of T dx. I'm going to put these on another board. Less than or equal to a constant F L F L1, and this is a constant 1 L1 intersect H1 F F times 1 plus T to the minus 1/2. So E of T dt E of T F is bounded by 1 plus T to the minus 1/2 F L1 intersect H1, same. And if I take both together, a derivative on F and a spatial derivative of F and a time derivative on E, that's less than or equal to a constant times 1 plus T to the minus 1 F L1 intersect H1. Okay. So now proof is going to be like this. We will, okay.
Sorry, Professor, the top line, the right-hand side is monoreal, so it's monoreal C, norm of F in L.
Oh, and H, no, H4. So it's this kind of high frequency, cheap high frequency estimate where we lose lots of derivatives and we don't care. Thanks. Yeah, that's important. Okay, so this is what we're shooting for. Let me put it down so we can see them all. Okay, so the proof. Okay, we start. We have S of t is 1 over 2 pi I PV of integral of gamma minus I infinity, gamma plus I infinity, e to the lambda t, lambda minus L inverse, okay, F d lambda. Okay, so now first thing we do is we move everything over like this. So we start out here somewhere. Let's say gamma naught. And we're going to move the contour. Okay, we know by the high frequency resolvent type estimates, we can move across the boundary as long as we have a bounded resolvent. Why do we have a bounded resolvent? Well, because we have high frequency damping. We know that we can do this. And this part I will discard. And this part I will discard. Not discard, but I'll put it into the high frequency term. And in the same way that previously we had a vertical line all the way down, and we used that to, I used this kind of cheap estimate using the resolvent identities to make it an absolutely convergent integral at the cost of spatial derivatives. And I said that was a poor man's Proust theorem, and it is, because you lose 4 derivatives and you get back what you would expect to get without loss. But here you see, I don't know what to do in the middle here. There's essential spectrum in my way. I can't go all the way across. I can't apply Proust theorem, and nor is this a subspace I can project away. This is infinite dimensional, and I don't know what it is. It doesn't have any simple way to project it out that I know, other than this. So I take this part, and I still get the same bounds, and I don't have to. I don't have the hypotheses I need for Proust theorem, but I don't need them because I'm doing something inferior. So I do that, and that takes care of this part. Okay, now I have, okay, so now I have some other terms. I can, for the explicit terms, I could just move them either to the contour at 0, or I could move them to the Fourier, over to the Fourier contour, which is the dispersion curve. I can do whatever I like. I've shown how to estimate the 2 principal terms. And one was a free-flowing heat kernel. That goes into S tilde. S tilde is basically like the constant coefficient bounds. It has the same bounds. And that's all I want. So I put those there. Okay. So free flow goes to S tilde. The error function goes to E. It's exactly, and what have I discarded? I've discarded something that is confined. I have a difference. This should really be in there, but for strategic reasons, I wanted to start at 0. And so I put this in. So, but what is this? This is something that it's 0 for time bigger than or equal to 1. So I can put that in, I have a bound, like that's much better than an exponential bound. So I can put that part also with, so chi minus 1 times this also goes with the error term. And then the last thing that I need is that, let's see. And then I need, okay, so now I need to, okay, so this estimate, we've already done for constant coefficients many times. So, so these are done. And I just need I need this estimate, all the estimates for E. Let's see. Yeah, I think I should, I think I need to put, sorry, I need to put L1. Because the part I discarded, it wouldn't work against L2, works against L1. But this also is harmless. Okay, so I just need to show, what do I need to show? I need dx, w bar of x, and then error function against f. So this was the first estimate. The first estimate was this one. So the L2 norm is bounded by this. No, sorry, the E. It's these. This one. This is the first one.
Correct. So this high frequency, you fix the contour.
Yeah.
And you just take, I mean, you fix the contour with real lambda.
Yeah. And I took only the high frequency part. Yeah, so I put those into the high frequency part. I'm going to call this other part where this cutoff, I'm going to throw that into the high frequency and call it high frequency because it's short time and it has the same bounds. But it really didn't come from that.
Then we integrate over the.
Yeah, you still have to integrate over these contours. But so remember that if I just, if I go all the way into here and just integrate on this part of the contour, the explicit integrals would be, it would just be the inverse of the Fourier inverse of a Gaussian, and it would give me a heat kernel. Or in the other case where I have the pole, it gives me an error function. There are some error terms. What do I do with the error terms? Well, I move the contour so that I get the error estimates without explicit computation in the way that I showed you before, or I think of station or the steepest descent, right? I just choose the intersection with the x-axis to give me the best estimate possible. It gives me the same estimate because for for a Gaussian, they turn out to be the same. Right? If I have Gaussian decay as I move away from the real axis, that just gives me a constant that integrates away, and I'm left with the value on the real axis, and that's giving me the same sharp bound as I had for the explicit computation, but now it accepts error terms.
The definition. Not the estimate.
Oh, okay.
Definition of SHL.
Hmm.
What's the precise?
It's going to be a number of terms. It's going to be the actual high frequency terms. So I'm going to throw this in and call it high frequency. There are some other terms. There are terms that are like e to the mu plus of lambda x minus y, e to the lambda t d lambda. where this was uniformly negative. And that I would just, so that there's more than one, there's actually more than one thing here, right? I've written them together, but there are terms, I spectrally decompose the matrix into decaying and growing parts, the stable and unstable parts. So there's an unstable part here and a stable part. It turns out the stable part, I can just move across. This has one sign everywhere. Everywhere, sorry. One sign everywhere here, and I guess it was everywhere. Yeah, it had one sign for real part positive, and it had one sign down until at least the branch point where the eigenvalues collided. So I can move that to a strictly negative gamma and go across. I can complete this arc. That one was analytic and perfectly well behaved. It didn't change, the real part never changed sign. No problem. I get exponential decay. I throw that into the high frequency part. So there are some terms I'm discarding. And then there are error terms because, well, this one's actually, there are different other terms that are discarded, like 1 plus O of lambda plus O of e to the minus x. There are lots of error terms that go in here. They don't matter. They're all uniformly bounded. They came from the conjugator, not from this. They came from the conjugation. They're uniformly exponentially decaying for all these lambda on any bounded set. So for sure, I can move it over here and get rid of this. That goes in the high frequency. So anything that looks like e to the minus theta absolute value of x minus y, I can just move it over and get an e to the minus gamma t times a nice bounded kernel. And that goes in the high frequency part. So that's, yeah, and likewise, there are some terms that came from, so this principal pole term that gave me this error function, remember, there was also a Taylor expansion there, so there were some errors there too. And those kind of error terms, I'll stick in S tilde. So S tilde is not only the free flow, it's everything that decays like the free flow. So I'm kind of combining things that have the same decay rates. So it's, yeah, and it's a pain tracking down every term. There are lots of terms, but they all one by one. And as you get to the last couple of terms, you get very nervous. Right? Because, well, maybe this one's going to wreck it, but they just all fit.
But you work with Z or you work with V?
By now we're back to V. We've translated everything back to V, and that's what gave us some error terms that looked like exponential decay in X or Y. So there are some error terms would be a factor of lambda, which gives us extra time decay, so that's good. Some error terms would be an exponential decay factor. Well, if we have enough exponential decay, we can move things into the left half plane and get exponential decay in time. So exponential decay in space will give us exponential decay in time by moving the contour. So those are also error terms we can deal with. And we just I didn't quite catch what you said. So the advantage of V, of Z. The advantage of Z was we could very easily write out this decomposition by variation of constants. It was very clear, I think, in the Z coordinate. Yes, and then, but we had to go back to the V coordinate to see that this is the thing that sits here. That was very important.
But the Z was also because you separated the behavior at plus infinity and minus infinity. No?
Yes, right, and that. So I mean, the Z was, yeah. So there was some. So when I change back, I have to undo that.
Z plus minus?
No, because no, they're complementary, but I do have to undo the transformation. So V is the same. There's no V plus or minus, but I'll remind you, V is equal to T plus or minus of Z plus or minus. So it's T plus Z plus for X positive. It's T minus Z minus for X negative. That's the key. And this is identity plus something exponentially decaying in X. So I've got some new terms coming in. And I also have to remember this is dx little z, little z and dx of little z. And this is decaying like a heat kernel. This is decaying like the derivative of a heat kernel. Okay, so these things get mixed up. And this is really v, which is little v dx v. So if I thought maybe I can just read off x derivative estimates from z, I can't quite because it mixes with undifferentiated terms. However, those coupled terms have an exponential decay in x. So, but that's what I have to pay for. It's like a commutator term, basically, but just seen in a different way. Okay. That's probably many people were thinking exactly that. Okay, but is that close enough to get the idea? Yeah, so we're distributing these things into different piles. And now the one thing that's left is I've got to get these 4 estimates, the bottom one here and these 3. And how do I get those? Well, it's quite explicit. So for instance, let's see, the first one. So here's the first one. I want that the L2 norm of this, not the L2 norm, just the L2, there's no, this is E of T, F, by definition. I want that to be less than or equal to F L1. But that's clear because this is the error function in Y and T. It's bounded. And this is in L1. So I have such a bound with constant. And now if I take the time derivative of an error function, I get a heat kernel. Okay, so now that's convolution, not convolution, that's the integral of G of Y T F of Y dy. I can bound that by L1 of F, L infinity of G. And the L infinity norm of a heat kernel is like T to the minus 1/2. But of course, I always have the option. So I think I wasn't quite careful enough. I did need H1 as well. Did I write it here? Oh yeah, I did. I wrote H1. Okay, good. Because I can do that, or I can do G L1 F L infinity, and that's less than or equal to G L1 constant F H1. And so that's how I get the 1 plus T. I don't want just I don't want a singularity. So yeah, check some cases. That's this one. And, well, okay, the time and space derivatives are similar. This is a derivative. This is like a y derivative if I integrate by parts. And that would be fine. That would be fine if, except I just told you that derivatives sometimes give not only time decay, but it might instead give an exponential decay in y this time. We should worry about that. But that can't happen because remember, I found out by looking at the solutions of the adjoint eigenvalue equation, this was not in the v coordinate, this was a constant times an error function. It wasn't dependent on y. So that y derivative, it's truly a y derivative of an error function, which is a heat kernel. And if I take both, I've got the time derivative of the spatial derivative of the error function, and that gives me like one derivative of a heat kernel. And if I take one derivative, the L infinity norm is now t to the minus 1/2. And that's why I get the, t to the minus 1, not t to the minus 1.
Just,
Yeah, it's not hard at all.
it has almost.
It doesn't have to, yeah, right. It's just properties of convolutions, not even convolutions. So, yeah, Holder estimates and decay.
Why is that E of t equal to this L0? It's L0.
L of yt,
Yes.
this one. Oh. L of yt is the error function of y plus a t over square root of t. That's what it was. And this is an important comment. Like if I took an error function and differentiated in space, I get a Gaussian. Okay, fine. But why do I say in differentiating in time gives me the same thing? It should be like when I take a time derivative of a heat kernel or something made out of a heat kernel, I should gain t to the minus 1. But I don't because of this. There's when I take the time derivative, I get an additional space derivative component, which is slower decaying. It's because things are space and time decay are space and time derivatives are roughly equal for a convected heat equation. They give the same decay rates, and that's why I get these bounds. Okay. So now I'm ready to prove. Okay, so I'm going to call this proved, even though, I know I left out many details. To really be sure, you have to do all those details. But now we will do the stability proof. Okay, any questions on what's stated here? Okay, so I'm going to follow very much the same formulation, the same setup. Okay, so maybe I better keep these, but I don't need the proofs. So nonlinear stability. And this is going to be similar to this equivariant stability result we proved. So I'll call it a refined freezing, or I like this term, instantaneous projection. That's the method we're using. Because instead of projection, that would be just L infinity, where this is constant. It's actually 1 over the jump in the shock. That's the time asymptotic projection. And that's what we used in the previous results. And there's no difference between, if you have a spectral gap, the difference between the time asymptotic and the instantaneous is exponentially decaying in time. It's quite absorbable in everything. But here, as I pointed out, it wasn't. The difference between this and the one that we're going to use, which is L of yt, or L of yt inner product with whatever. The difference between these two is non-decaying in time against L2 functions. So that's important. And even against L1 functions, it's non-decaying in time. So this is the one we want to use, because we're not going to be able to close a stability argument if we have non-decaying elements. And basically our strategy is the same. Before we had a projector, this E of t, which was it looked like this, but it was the time asymptotic version. And basically the idea was that didn't decay, but everything else did decay. Well, now that wouldn't be true, but we found something very similar that does decay. Sorry, for which if we remove it, everything else does decay nicely, but it's just not, it doesn't look the same. We're sort of tracking the effect of different terms. And that reminds me that I did want to draw one picture for you, and this is the picture. So we have this picture of basically a diffusion wave moving in toward the shock. Okay, so mass is accumulating at the shock. It brings mass. How much mass does it bring? Well, that's the error function against a little piece of mass. The error function at, right, if we integrate from minus infinity out to, sorry, if we integrate this from minus infinity out to 0, that's the mass at the shock, and that's actually the same error function that's moving along. Oops, I did it backwards. It's 0 to the left. As it strikes the shock, the mass accumulates. How much? The integral in space of the Gaussian. But that's an error function. It's exactly this error function. And that's what shifts the shock. So this actually makes a very good intuitive sense that this is how much mass, how much the shock has shifted at time t. Okay, and then, but it varies. Okay, so now we'll set V defined as before, W of x plus delta of t, t minus W bar of x. And that gives us dt V minus L around W bar. The linearized operator around W bar is dxn minus delta dot V minus delta dot dx W bar. This is exactly the same as before, nothing different. Okay, now we'll do variation of constants or Duhamel expression. So we get V of t is equal to S tilde of t V naught. Oh, now I've done something bad. Let's see. Okay. Let's call S hat equals S high frequency plus S tilde. Together, these obey all the bounds that we had for the constant coefficient problem. And okay, okay, now you'll tell me I left out one term. Where's this term? The trick is I'm going to hit this term with the whole solution operator, because I know that this is a function of time alone. If I apply the solution operator to this, though, this is a stationary solution. It's unchanged. So this contribution is negative integral from 0 to t of delta dot of s ds. And that's from both s hat and the remainder s tilde. That's the whole solution operator. Okay, and then, but now I get E of t applied to V naught plus integral from 0 to t E of t minus s dx n plus delta dot V of s ds. Let's see, this was s ds, that's everything. Okay, this, by fundamental theorem, is integrable, and it just gives me negative delta of t plus delta of 0, but delta of 0, I'm going to take to be 0 because, right, this is 0 at, I've arranged that by my cutoff, I made E of 0 equals 0. By definition. So if I set delta of 0 to be 0, I've balanced the initial conditions. I'm free to choose this, and just as I was free to put a cutoff in there. It makes life easier. Before, I had to choose my initial data by some implicit function theorem to achieve that. Now I'm just achieving it by force. And so I'll just set this to be 0. I want to get rid of this non-decaying term. So that's another way of doing it. I'm not just, I'm not enforcing vanishing of a certain projector. I'm just going to, it's just a very operational definition. I want to get rid of the bad terms. I get rid of them. I set this equal to 0. So I define, and this is implicit now, not explicit. I'll define delta of t to be equal to all the rest. And, I have to make sure I have to show that that makes sense. And then delta dot of t will be dt e of t v naught plus the integral 0 to t of e of t minus s against dx dt, sorry, dt of e against dx n plus delta dot v of s ds. So I'll keep this, and I'll keep, now this is gone. So I'll keep these two. This is my new system. It's a system in V and delta dot. In the old version, we were able to be a little bit more clever, and we could define delta dot as in terms of V explicitly. And so that was nicer, but it wasn't necessary. We can do this. Delta dot should be dt of E against the initial data plus the integral of dt E of t minus s against the forcing term, which is dx n plus delta dot v. No, I didn't. I imposed this. I set all these terms to be 0. That gave me an equation for delta, and then I just differentiated it, noting that at 0, at 0 I get let's see what. I know there's 0 is fixed. There's a time derivative up here, but that gives me an E of 0. E of 0 is 0. That's why. That's okay. Thank you. Yeah. If I that's another reason for choosing that that cutoff to make this work. So everything works well together. Right. And now I have, so by differentiating this equation using the cutoff, I have this expression. Okay, so now I just need to solve this system together. And okay, so now it's a matter of estimates. Okay, so my proposition is, now I have to be careful. I want to keep those estimates. Okay. Okay, V of t, H5 is less than or equal to, uh, uh, oh, I have a nonlinear damping estimate. Okay, there's a new term that comes in here. It's just from handling, it's the same energy estimate. There's now a delta dot. There's a delta dot, basically dx v against dx squared v, that's 0. And there's a delta dot dx v against dx squared w bar. And this one we just write, we put the derivative all on w bar. And we see that this is less than or equal to delta dot VL2. And that's less than or equal to delta dot squared plus VL2 squared by Young's. This is a term that we allow, that's what went into this error term. And so the delta dot squared has to go there too. But it's harmless. It's going to turn, delta dot is going to decay faster. All right. And I will just will allow me to just go a little farther because we're going to have a long break. I'll give you the bootstrap argument. So we set alpha of t equals soup, 0 less than or equal to s less than or equal to t, 1 plus s to the 1/2 delta dot of s plus 1 plus s to the 1/4 v h s squared, h5. And we say that alpha of t will be less than or equal to a constant, v naught L1 intersect h5 plus alpha of t squared. And let's see, I think that, okay, so the S tilde terms as before. They go essentially as before because we have, where's our Duhamel? Oh, sorry, not the S tilde, but the V. The V terms go as before. And where are, here they are. Because now it just looks like it's identical to what we had before, except we have one slight difference. We have a delta dot V instead of V squared. But delta dot is going to decay, delta dot is going to decay faster, t to the minus 1/2, whereas L2 norm of V decayed like t to the minus 1/4. So when we had V squared, we basically took L1 of that term. We got L2 norm squared, which is minus 1/2. We've already got that from the delta dot. Why are the delta dots faster? Because notice here we had everywhere the bounds on S tilde were -1/4, -3/4. These are -1/2 and -1. So we gained this 1/4 power. I think I'll just redo this part of the calculation after the break, but that's enough to kind of see how it goes. We removed the bad part, now everything works. But okay, yeah, I think we'll do it more carefully when we have time. And that won't be, hopefully a month break won't be terrible for that, because we have the bounds. We'll start with the bounds and redo it. Yeah, it's a nice argument. Okay, so thanks for your attention and patience. And we've got the next meeting, though, is going to be March 2. There's a 2-week break for us because I have to return home for some duties in the second week.
Time to study.
Yeah, you have time to study. And
You're welcome.
Yeah.
It was subtle to have this x plus delta and choose delta in the wise way.
yeah, yeah, you can imagine this is like a fixed point iteration, right? This was trial and error many times till it worked. Yeah, yeah. And like even yeah, why did I cut things off at 0? That was really, that made everything work nicely. Well, for the burgers example, it happens to vanish at 0 by coincidence almost. So that was some luck. So we wanted to look like burgers, so we'll cut it off. Yeah, anyway. Well, you know how it goes. You just keep jiggling it till it all works. Okay, any questions from online? Okay. All right. Well, have a good break, everyone, and see you after. We'll see you tomorrow at Clean Start. Yeah.
What do you think? Not to sell.
You mean the one supposed to be tomorrow?
Yeah.
No, no, they apply, the analysis apply. I mean, they occasionally do that, but only, I mean, that kind of room is set up for streaming, but they do it very rarely just for kind of departmental councils and stuff like that. Because apparently it doesn't work so good.
Oh, yeah, it's kind of a pain, really. But unless you have pain and this army of people doing it.
Yeah, sometimes the projector doesn't even work, so. Really? So.
So you guys were, oh. Yes. This would be very lonely without you. Will you be around over the break?
Yes. It's the best moment to work.
Yes.
Right? No teaching, no mess. Yeah.
For your achieve for country.
Yeah, but that's kind of measure 0. It is it's not a problem. It's the analysis one first year which is destroying me. I really like.
How many students?
220. But the problem is that they're not. They're supposed to, I mean, drop the course, but they don't. So.
Yeah. Oh, this.
But is it going well?
Sorry.
Is it going well?
I think yes. I mean, I think it's weird. I mean, like there are 220 students enrolled, but like 90 or 100 of them are taking the lectures. And so, like the average in quizzes is like 50%. Pretty low, right? It's supposed to be kind of the analysis one with honors. So I mean, kind of the high-end course. I think it's very low average. The weak students should have already
Right.
dropped and gone to other places. They don't. Like last time I graded all the stuff. I mean, I was saying harshly, like fairly, and had to change like my grades to
I just,
Yeah, I keep adjusting up.
yeah.
Yeah, because I feel so bad. But I had a music teacher who told me a joke that I think perfectly fits this. So, he says there's a guy and he signs up for, a mail order, trumpet class, learn to play trumpet, 10 days. Back in. How's it going? You're on day 9. How's your performance? He said, I can't play at all. I can't wait till tomorrow. I think that's these guys that they're failing out.
No, I think they're really in that kind of state. But I mean, I didn't do my undergrad year, but as far as I know, they might have some financial trouble.
Well, that is the other issue, right? If you drop it, you drop below the credits for your stipend. Yeah, so.
Yeah.
so that's the reason why they don't want to.
I think they're sticking to the course because they hope at the end there will be kind of massive curving. And so eventually they skate with a 50, but
Yeah.
like,
Well, but some also even, he's like, if they just stay till the end to fail, they still get their stipend.
yeah, I think they also need exactly because they need to do enough credit. I mean, no matter if they
Yeah.
get an app.
Unfortunately, that's very bad.
Yeah.
Yeah, it's,
So
I've seen it. No, I don't know how it works here, but at home, that happens.
yeah, I think there's something like there's also here. Anyway, I mean, these students are like, I don't know, or maybe they're really enjoying the course because the bottom line is that the instructors are very artistic in it, also married. And the lectures are very nice and whatever. So maybe, they're afraid that if they drop, they take, I don't know, 137.
And then
There's not gonna be the same fun.
What's the topic right now, so what's the topic for them?
Now, well, they just learned the fundamental theorem of calculus
Oh,
and
okay,
stuff
so
like
this
that.
is just, okay. Help one.
Yeah, it's called analysis one because essentially they use some proofs.
Oh,
It's a proof course. Yeah, it's calculus with proofs essentially.
okay.
And we have three calculus classes. So there is the completely proofless class, the with proofs, calculus with proofs, and then there is this one that should be kind of, the upper, say, high level, but
no.
We had this with proofs. You had disappeared because of high school calculus courses.
I think it's a good idea.
Actually, I think we should actually.
It's a good idea to do what?
High school.
Yeah, I think it should be like that. And if I was a student here, I think the best class to take it would be calculus with proofs because you always have time to take general topology, learn what a compact set is, the Bolzano bias or Stephen.
Also, you have to notice that they don't learn much in high school. Like they do really like basic stuff. So when it comes to uni first year, there are a bunch of things that they have to learn at
Yeah.
the same time.
Mhm.
It's very difficult. They have to change everything.
I think so. Because now essentially this
But
course.
they're doing it. I think that many complain that the math level of high school student in Ontario is very
Yeah.
very start doing it now.
But in this course, this kind of supposedly fancy course it's the level is below the level of my last year as a high school.
Oh,
Like my grade 13, because Italy is 13 years, was harder than this. So it's weird. Anyway, it's kind of eating up my time. That's the problem. As far as I'm concerned, they could lecture them, functional analysis, but
so it's not the politics that concern you, but.
no, absolutely. Also
the
because
practical,
it's above my pay grade, right? So,
There's something beyond.
no, I agree, but well,
It's okay. Yeah, actually, teaching is. I think we did it together for APM. Really hard to really want to give much, but the students don't want to. That's the thing.
you must go
That's
victory. You must victory the course. That's my
my students.
But even there, you know.
Yeah, they complain.
Oh
Yeah.
my God, like there, like
Yeah.
even repeating the same exam
Yeah.
every year doesn't help.
They complain.
Many
but,
people
you know, like,
fail.
because quizzes have like row A and row B. En ze toen zag ik row B zaten. Well, sis, that's not a tell. You been education, you're that's not more of infection. It's not going to actually don't be here.